Alrighty, welcome to episode number 1, season 1. We are looking at 1.1, arithmetic sequences. This is on page 2 of your workbook. But before we get started, gotta be honest with you here. I'm going to be challenging you all the way through this course. You're going to have to be doing a lot of work. This is what it's really all about right here. As teachers, we sit in the staff room there. We figure, hey, what's the best way to torture these kids? Math is always a great one. Looking for the most excruciating algebra problems that we could possibly give you. So with that said, let's get started. We're going to be talking about sequences here. We need to know what a sequence is. Let's look. When the numbers on these plates are arranged in order, the differences between each number and the previous number are the same. That's the key there. So we're looking at, we know those two, and we got to figure out what's in the middle. So, good idea is to pause right now and just see what you can do on your own first before seeing what I do. And you'll always learn a lot more if you try things before you see me doing them. So pausing it is a great strategy with that. So the way that I'm going to go through it is to say, I don't know what my difference is, but I know that the difference is going to be some number. It's the same, so I'm going to make it x. So I'm going to say let the difference be x. And I know that all the way has to be 35 minus 11. Well, that 35 minus 11 has to be equal to 1, 2, 3 x's. Or you could have thought of it as 11 to start with, plus the 3 x's is going to give me 35 at the end. However you want to go through it. And now we just solve for our x value. So either way, 3x is equal to 24. I subtracted the 11 over to get this, really. And then divide by 3. So then x is equal to 8. Now that you know that it's going up by 8, you can just add 11 plus 8. So that's 19. And then 19 plus 8, 27. Always do the last one. 27 plus 8, does that give you 35? Sure does. Good, that's the right one then. And let's construct the understanding here. Let's bring and make those connections. Again, I highly recommend you pause now, you do this one yourself, and then see if you got it right. Second took guitar lessons. The first lesson cost $75, including the guitar rental for the period of the lessons. The total cost for 10 lessons was $300. Suppose the lessons continued. What would be the total cost for 15 lessons? So let's start highlighting here. So we've got 15 lessons, we got $300, 10 lessons, we've got $75. All right, let's make some kind of a statement with that. So that first lesson is an anomaly because you had to rent. So this $75, that's different than every other lesson. So out of these 10 lessons, the first lesson includes a guitar rental. So I'm going to pull that one off. So then I'm going to talk about the next 9 lessons. So I'll say next 9 lessons equals, that was the $300 for the first one, for the 10, and subtract off that $75 there. That's going to give me $225. So all the next 9 lessons, $225. Let's find out how much each one of those is. Well, that means divide. Let's divide it. 225 divided by 9. Hey, that's $25 per lesson. So I've asked you how much was it to rent the guitar? Well, we know out of that $75, 25 was for the lesson. Hey, $50 for renting of that guitar. Good deal. Now I want to know, continuing the lessons, 15 lessons. The first 10 cost $300, so that means another 5 at $25. Those other 5 lessons, that's $125 right there. Add that to the $300 that you already paid for the first 10. $425 for 15 lessons. Nice. So what we've been talking about here now is sequences. So what is a sequence? A sequence is an ordered set of numbers. That's it. You put it down. Whether or not the order is the same between each doesn't matter. It's just a bunch of numbers in some order. That's a sequence. So really, any numbers that you can write down makes a sequence. We put commas in between each one of them. That's a sequence. A term, every single one of those that's separated by the comma, that's a term. So term 1, term 2, term 3. That's a type of sequence right there. But if you notice, the difference between each one of them is not the same. It goes 1 to 1, then to 2, then to 3, then to 5, then to 8. Whew. But there is actually a pattern going on in there. See if you can figure out what the pattern is yourself. All right, in an arithmetic sequence, the difference between consecutive terms is a constant. This is where we're going to focus right now, arithmetic sequence. That was the title of this lesson. The difference is the same, so we call it a common difference. And we represent it by the letter D. That's called a parameter. And you can see there, if we've got 4, 7, 10, the way to find your D value is to subtract any two consecutive terms. So, for instance, we can go T2 minus T1, T3 minus T2, T4 minus T3. And you'll always get the exact same number. If you don't, it's not an arithmetic sequence. That's got some dots sitting there at the end. And we're talking about those three right there. Those mean that this is an infinite sequence. It goes on forever. It does not stop. And sequence notation is going to be exactly the same as function notation. It just looks a little bit different, a couple different rules. But we can graph it the exact same way we've graphed any before this for functions. So we've got n as one variable, and the other variable is tn. So there's your two variables. Instead of x and y, we've got n and tn. The value for this is t1. The n value is 1. It's the placeholder. N is the place or position of the term. Tn is the value of the term. So 1 is our n value. 4 is the value. So again, 1 is your n. 4 is your tn. And we can plot each one of those. So you can then see that at n of 1, the value is 4. At n of 2, hey, it's 7. At 3, it's 10, 13, 16, 19. And notice this. We don't connect the dots. I can't have term 1.5. Because if I put anything in between these two numbers, halfway in between, that would have been term 2, not term 1.5. So we can never talk about in between. So we've got always in sequences, it's going to be just dots, discrete data. Now the first question we're going to discuss in class is going to be why? Why is the domain the natural numbers? So put down something there for why. Now in a sequence, the common difference could be any real number. It doesn't have to be a natural number. It could be 3.46. Doesn't really matter. It could be negative. That's fine as well. And there's some examples. First one is increasing. The reasons it's increasing is because the difference is positive. In the second one, it's decreasing, a negative, meaning it's going downwards, whereas the first one was going upwards. So now let's split that halfway. Not positive, not negative. What happens if the common difference was 0? What would that one look like? That'll be the next question that we discuss in class there. So make sure you write something down, have something prepared to discuss with. All right, let's get into the work now. Let's talk about, just so you know where you are, you're on page 4. And we're in the left-hand column there. So write the first 6 terms of an increasing arithmetic sequence. Hey, you get to choose. So what do we need? We need a starting point. All right, what T1 do we want to use? Hey, let's go minus 20. Great. And we need to have some difference, the common difference between to get us to the next one. Let's just choose 2. Doesn't matter. These are all just whatever you want to choose in this one. Okay, so first one, hey, we know is negative 20. We start there. Negative 20. Then the second one is going to be, that's T1. The second term is going to be T1 plus our D value, which is negative 20 plus 2. Okay, the next one's going to be T3, and that's going to be T2 plus the D value. Okay, so we got negative 20, we've got negative 18, and then now we're going from negative 18 and adding 2 more. But wait a minute. Well, what if I didn't really want to find T2 before I found T3? I could have said the negative 20 plus D plus D. Or in other words, negative 20 plus 2D, which would have been negative 20 plus 2 times 2, hey, plus 4. Negative 20 plus 4, hey, that's negative 16. Oh, yeah, that works too. Let's go to the next one. After that, I'd add 2 more. Or going back to the first one, I would say, change my order there, move it down. I would say that I can have T4 being that negative 20, or that T1, plus D plus D plus D, or 3D. Ooh. So that would be negative 20 plus 2, 2, 2. Oh, that's 6. Which gives us then negative 14. And then the next one, following the same pattern, we know it's going to be, hey, going on another one, negative 12, but that would have been negative 20 plus 8, or T1 plus 4D. And then the last one would be negative 10, which would be negative 20 plus 10, or T1 plus 5D. Let's switch it up. A decreasing one. So I know that if it's decreasing, my D value has to be negative. Let's pick negative 3 for the fun. Let's pick a T1. Any suggestions there? Sure, 100 sounds perfect. Let's do that one. So 100 is our first one. The second one, we're going 100 plus a negative 3. Don't say minus 3, say plus a negative 3. We're always going to add the difference, either if it's positive or negative. So we're saying 100 plus a negative 3, which is really saying T1 plus D. And then the next one, we could again start at 100, and we would be plussing a negative 3 and another negative 3, which would be plus a negative 6. Or in other words, T1 plus 2D. Oh, look at this. It doesn't really matter what's going on, what we picked. So the next one was 100 plus a negative 9, 100 plus a negative 12, 100 plus a negative 15. That's going to give us 100, 97, 94, 91, 88, 85. Now, could you have done it just quicker without writing all these things down? Of course. But I'm trying to make the connection for you to move to the next point here. So looking at the general term here, what we're doing is we're taking our T1 value and we're adding a difference to it, the difference which was 4. And notice this is the big thing. In T1, we're adding 4 times 0, or no other 4s. In T2, we're adding 1 4. In T3, we're adding 2 4s. In T4, we're adding 3 4s. So it's always 1 less than the term number. That sounds awfully a lot like a formula. So we're starting to get into what's called a general term. Common distance is 4. The general term is Tn. It is what, for any term number, the nth term is 3 plus 4 times n minus 1. But we don't want to leave it like that. We want to simplify everything in mathematics always. So take it. What you're going to be doing is distributing that 4 in. So you're going to get Tn equals 3 plus 4n minus 4. And now, hey, we got common terms there, 3 and negative 4. So we're going to have 4n minus 1. That's where I want you to take it to be able to leave it as. So the formula that we're going to be using, you can see at the top of your page 5, Tn is equal to T1 plus d times n minus 1. All right, let's try it out here. For this arithmetic sequence, they're already telling you that the d value is there. You just got to find it. Determine T15. All right, I've got a formula there. Anything that's formula based, put it on the side. Tn equals, T1 equals, d equals, n equal. You got 4 things you got to know. In order to solve for one of them, you need to know the other 3. So let's figure out what we know. I'm looking at it and saying, ooh, this is Tn, so n is 15. I'm looking for the 15th term. D, ooh, I need to know what that is. That's the difference between these two. Always the second one minus the first one, not first minus second. You go 10 minus 3, which gives me 7. Do a quick check. 17 minus 10, hey, that's also 7. So my D is 7. The D is saying, what am I adding to get to the next one? I'm adding 7. T1, got to know the first term. Hey, that's 3. I see it there. And Tn, that's what I'm looking for. I'm looking for T15. So let's plug in what you know. T15 equals 3 plus d, 7, times n minus 1. And now we just work it through. So we've got 15 minus 1, 7 times 14 is 98, plus 3, 101. So T15 is 101. Boom. Oh, something I forgot to mention. Start with your formula before you even get started. This should be written like right before it, and then you fill it in as you go through. All right, 220 is somewhere in there. Which term number is it? Which term? Hey, that's asking us about the position, the placement. So we've got, again, start the same way. T1, D, N. Let's figure out what we know. I know that my T1 is 3. It's still there. And I know my D is 7. I'm looking for which position? I'm looking for N. So I must know Tn. Oh, yeah. The value is 220. There we go. Let's go through the thing again. Start with your formula. Tn equals T1 plus Dn, whoops, minus 1. There we go. And fill in what you know. I know that this is 220. I know that this is 3. I know that's 7 and minus 1. Perfect. Let's start solving for n. So I'm going to recommend going about this way. Less mistakes get made this way. Distribute in your 7. So you'll get 220 equals 3 plus 7n minus 7. And then start combining your like terms. So we get 220 equals 7n minus 4. Hey, let's add the 4 up and over to this side. Gives us 224. So 224 equals 7n. And let's divide over that 7. And for those of you who didn't see what I did there, I went plus 4. And then now I'm dividing by the 7. Which gives me a lovely 32. Magic number. Hey. And you probably say to me, hey, why are you saying that's a magic number? Well, we got Magic Johnson, number 32, one of the best basketball players ever. Now, next question we're going to be talking about, what if I said 246? How do you know that's not in this sequence? Figure out how you'd be able to tell. Now, for the next question there on page 6, I'm going to stop talking for a moment. I'm going to let someone else explain their example, number 3. So this is the example that's already done for you in the book there.
Two terms in an arithmetic sequence are T3 equals 4 and T8 equals 34. What is T1? I'm going to draw a diagram to help me find T1. I'll start by drawing boxes to represent the terms. Since I know terms 3 and 8, I'll draw 8 boxes and label them T1 through T8. I know the third term in the sequence is 4, so I'll write that here. I know the 8th term in the sequence is 34, so I'll write that here. I'll let D represent the common difference. I see from the diagram that if I start at the third term, I have to add the common difference 5 times to get to the 8th term. T3 equals 4 and T8 equals 34. Now I'll subtract 4 from both sides of the equation, which gives me 5D equals 30. Finally, I'll solve for D by dividing each side of the equation by 5. So D equals 6. Now I can find T1. I see from the diagram that if I start at T1 and add the common difference 2 times, I get to T3. T1 plus 2D equals T3 is the same as T1 equals T3 minus 2D. T3 equals 4 and D equals 6. 2 times 6 is 12, and 4 subtract 12 is negative 8. So T1 is negative 8.
Whoa, that was pretty good. That was pretty good. Guessed into the classroom there. All right, so let's do ours. Let's follow the same process. All right, so we got 7 terms. So 1, 2, 3, 4, 5, 6, 7. I'm just going to use blanks. It's easier to write. 1, 2, 3, 4. There's T4, 5, 6, T7. I know that one's 23. I know that one's negative 4. So then I've got 1, 2, 3. 3 Ds to get me from negative 4 to 23. So 3D is equal to 23 plus 4. Or 3D equals 27. Then we divide by 3. So D is equal to 9. Good, got that. Now we can just back it up. Subtract 9, subtract 9, subtract 9. Or in other words, we're doing T1 is equal to T4 minus 3Ds. Negative 4 minus 3 times 9. And that'll give us negative 31 when we punch her in there. Done deal. All right, the comet Denning Fujikawa appears about every 9 years and was last seen in the year 2005. Ooh, how does that make it? When are we going to see it next? Okay, so should we see it in 3085? Or not? I know I'm not going to see it, but maybe some of you will. That's how timeless this video is going to be. So notice that it's saying that it appears every 9 years. Hey, that means that we've got an arithmetic sequence. And that's our D value they're telling you right now. So it's last seen 2005. That means T1 is 2005. Our D value is 9. We've got Tn and we've got n to figure out. They're giving us this year. That's Tn. We're trying to find find n. So let's start there. Formula. Formula is Tn equals T1 plus D n minus 1. Always start with your formula, then substitute in. 3085 equals 2005 plus D, which I said was 9, n minus 1. And again, even though this is not the only way to go about it, less chances of errors that I find, distribute that in. So 3085 equals 2005 plus 9n minus 9. Let's combine our like terms there. And that gives us 3085 equals 9n plus, what is that, 1996? Hey, subtract that over. And we get 9n is equal to 1089. Divide by 9. And let's see what we get. N equals 121. So the question now is, should we see it in 3085? Well, yes. That'll be the 121st time that it's come around for the Earth to see. Unless, of course, it crashes into something or anything like that happens. Or we've blown up our Earth by then. Which I sure hope not. So the answer here is yes, we should see it. And the big reason is because, hey, that's a whole number. It's exactly the 121st time we will see it. All right, page 7 there. You've got 3 questions. I want you to jot something down. Come to class prepared so that we can then talk about these 3 questions. All right, see you in class. You made it through video number 1.